Here we have a 3 by 3 system of linear equations. So again, 3 equations, 3 unknowns, and I'm going to solve it. And I'm going to solve it by getting that sort of stair-step look. So I want to get a 0 here and here and a 0 here. There's already a 0 there, so that's nice. So this is partly done for me. So I'm going to go ahead and get rid of this x by adding equation 1 to equation 2. So in this move, I'm going to do this plus this. So I'm doing something to equation 2. That's a negative 1. So the first equation isn't going to change. The third equation isn't going to change. But the second equation is going to change. So it's going to be this plus this is 0. This plus this is still the 3y. This plus this is the negative 3z. This plus this is 0. Oops, equals 0. So now I have the zeros here and here. I'd like to get a 0 here. I'm going to use this equation to get rid of this y, but I can see that this equation can be written a little bit more nicely because I could multiply through by a 1/3 and not introduce any fractions. So 1/3 here, multiplication would be y minus z, and then 1/3 times 0 is 0. So I'm going to multiply equation 2 by 1/3. And so you'd have x minus 3z equals negative 1, y minus z equals 0, y minus z equals 0. And just listening to me say that, you probably noticed that you have 2 copies of the same equation, essentially. But let's go about this as though we didn't notice and just continue on our way getting that stair-step look. I want to get rid of this y, so I'm going to do add negative 1 times equation 2 to equation 3. So that's going to be my next move. So I'm doing something to equation 3, so equation 1 is not going to change. Equation 2 is not going to change. But equation 3 is going to change, and it's going to change radically. Because you do this plus a negative 1 times that is 0. This plus a negative 1 times that is 0, so you get a 0 over here. This plus a negative 1 times that is 0. So you get 0 equals 0. This equation is always true. True. So it really doesn't add anything to the system. So your system really boils down to x minus 3z equals negative 1, and y minus z is equal to 0. This is what they call an underdetermined system, because it has fewer equations than it has unknowns, which means that, and it's written about as nicely as you can, no matter what you try to do to clean this up. Like if I tried to get rid of this z using this equation or this z using this equation, I would introduce a y into this equation or an x into that equation. So no matter what you do here to try to make this system nicer, you're actually going to make it uglier. So this is about as pretty as it gets. And you know, when you solve a system, as we've done before, if it's got a solution or solutions, you want to write it as x equals something, y equals something, z equals something. I can sort of do that here because I could solve this first equation for x and get x equals 3z minus 1, y equals z. But I can't, z isn't equal, there's no z can be anything. And whatever z is, y is equal to that same anything. Because y is equal to z. And whatever z is, that anything, x would be 3 times that anything minus 1. Of course, we don't generally use the word anything. You usually write these solutions when you have infinitely many solutions like this, which is the situation. You usually use a parameter. So instead of saying z can be anything, we usually say z is equal to some parameter like t. And then y is equal to t. And then x is equal to 3t minus 1. And so here you have infinitely many solutions. Because you give me any value for z, any number for z, I can give you one solution. So if you tell me, all right, my favorite number is 4, say, then the solution z equals 4, y equals 4, and x equals 11 would work in this system. And if you like say -5 is your favorite number, then -16, -5 is another solution. So this is a case where you have a 3x3 system with infinitely many solutions. And what's nice about this is you can actually check this by plugging this solution back into the original system. So the first equation says, this will be my check. The first equation says you take x, that's 3t minus 1, take away 3 times z, which is t, and see what you get. 3t minus 3t is -1, and that's what it says on the right hand side, so that works. Check in equation 2, you get -3t minus 1, because that's our x, plus 3y is t, that's equal to -3t plus 1 plus 3t is equal to 1, which is what you have on the right hand side there. And equation 3, I hope, will also check. That one obviously checks. Y is equal to t, z is equal to t, that is definitely equal to 0, so that checks. And so here's a case where we have infinitely many solutions. And this is called the solution here we've written in parametric form. And this is a nice way, really the only way to write the solutions to a system of linear equations that has infinitely many solutions. Now depending on the system, if you have a big system like, say, a system with 5 equations, you might have 2 or 3 free variables, in which case you'd have to have 2 or 3 parameters. But the idea is the same no matter how big it gets. And we'll look at stuff like that later on the semester. Later on in the semester, like later this week maybe, or next week. Okay, very good.